Your app lets people upload photos, 200,000 of them so far, about 2 megabytes each. That is 400 gigabytes of pictures. And right now, they are all sitting inside your database. On day one, that felt tidy, everything in one place. Then, the nightly backups started taking 2 hours. Let me show you where those bytes should actually live, why moving them is the easy part, and the 5-minute link that keeps them private once they are gone.
First, look at what you actually built. Your real data, the users, the captions, the timestamps, is about 20 gigabytes. That is the part your app queries all day. Then, the photos went in. Now, the database is 420 gigabytes, and almost all of it is pixels that nobody ever searches. And a database is not a warehouse you fill once and forget. It gets copied constantly. Every night the backup runs, and it has to pull all of it through. 20 gigabytes would take about 6 minutes. 420 takes closer to 2 hours. The same thing happens on every restore and on every standby copy you keep for safety.
Here is the code that gets you there, and I want to be fair to it. You add one column. In Postgres, it is called BYTEA. In other databases, it is called a blob, a binary large object. Both mean the same thing, a bucket of raw bytes glued to the row. You read the file, you hand it to that column, you commit, and it works. One place to look, one backup to run, and if the upload fails, the whole thing rolls back together. For a weekend project, this is genuinely the right answer. It is not a beginner mistake. It is a good decision that quietly stops fitting.
So here is the trap, said plainly. A database is not a file server. It is tuned for small, structured rows, things you filter, sort, and join. Every byte you put in it gets backed up, copied to the standby, and pulled into memory. Reading one photo means dragging 2 megabytes out through a database connection, and connections are the scarcest thing you own. Meanwhile, the cache that should be holding your indexes is holding somebody's holiday picture. And after all of that, you still cannot put a content delivery network in front of it, and you still cannot stream video out of it. So the fix: send the bytes somewhere built for bytes. That is object storage. Amazon S3 is the famous one, but every cloud has one, and so do the cheap independents. You make up a name for the file. That name is called a key. You push the bytes into the bucket under that key, and then in the database, you store the key. That is the whole change. 60 characters of text instead of 2 megabytes of binary. The photo did not disappear. Your database simply stopped being the thing that holds it and became the thing that remembers where it is. Look at what that does to a single row. Before, the row carried the entire file, 2 megabytes, sitting in the table, in every backup, in the cache. After, the row carries a short string of text, about 60 bytes. The 400 gigabytes did not vanish. They moved into a bucket, where storing them costs around $9 a month instead of $40, and where durability is measured in 11 nines. That means if you handed it 10 million files, you would statistically expect to lose none of them. Your 420 gigabyte database is 20 gigabytes again. And there is a second win that is easy to miss because it is about the path the bytes take. With the file in the database, every download goes the long way round. The browser asks your server asks the database. 2 megabytes come back into your server, and then your server pushes those same 2 megabytes out to the browser. Every byte crosses your machine twice and holds a connection open the whole time. With object storage, the browser goes straight to the storage, usually through a content delivery network. That is a fleet of caching servers spread around the world, keeping a copy near the user. Your server hands out one short link and steps out of the way. A few hundred bytes of work instead of 2 megabytes. But now we have a problem, and this is where a lot of tutorials quietly cheat. A bucket is private by default. Nobody can read it, not the internet, not your users. So how does somebody see their own photo? There are 2 obvious answers, and both are wrong. The first is to make the bucket public. Now anyone holding a link can read anything. Keys get guessed, scraped, and shared. And you are one checkbox away from a very bad week. The second is to have your server fetch each file and pass it on. That is safe, but every byte is crossing your machine again. You did the whole migration and kept the bill. You need a third answer. Here it is, a pre-signed URL. Your server does not send the file. Your server writes a link and signs it. Look at the code. Somebody asks for upload 42. You look up the row. You check that this person actually owns it, and notice where that check lives. In your app, in your language, right next to the rest of your rules, not buried in some storage policy you will forget about. Then you ask the storage library to generate a signed link for that one key, valid for 300 seconds. Not a single byte of the photo moved through this function. You did some arithmetic and returned a string.
So what is actually inside that link? 3 things. The first part says which object, one specific file, not the bucket, not a folder. The second part says how long, 5 minutes, and then it is dead. And the third is a signature, computed with a secret key that only your server holds. The storage service checks that signature when the link arrives. If anything was edited, a different file name, a longer expiry, the arithmetic no longer matches, and it is refused. So the browser can take that link and go straight to storage, and storage will serve it, because it can prove your server said yes. The bucket never opens. One temporary key does.
And the same trick works going up. Instead of your users uploading through your server, you hand them a signed link to upload with, and the browser sends the file directly to the bucket. But that raises a fair question. What stops somebody pushing a 900 megabyte file or a program renamed to .jpeg? You attach conditions when you sign, a maximum size, an allowed file type. Those conditions are baked into the signature, so the storage service enforces them for you at the door. The oversized file is refused before it ever becomes your problem. And keep the expiry short. 60 seconds is plenty for a form. A link that lives a week is a link that ends up in somebody's chat history. So the arithmetic, the same 400 gigabytes of files. Before, a 420 gigabyte database and a 2-hour backup window. After, a 20 gigabyte database, a 6-minute backup, and a bucket costing around $9 a month. Nothing was deleted, nothing was compressed. The bytes simply went to the tier that was built to hold them, and the database went back to being a database. So the whole thing in 4 lines. A binary column in the database works, and it keeps working, right up until it does not. Object storage is cheap, extremely durable, and sits behind a content delivery network. The database keeps a key, a short reference, never the file itself. And pre-signed URLs are how you serve a private bucket. One object, a few minutes, signed by your server. Bytes in the bucket, reference in the row, signed links in between. If that made pre-signed URLs click, hit like and subscribe. I take one concept and go all the way down to the code, every time. There is a 90-second version of this in the description, if you just want the summary. Next up, what a content delivery network actually caches, and the one thing it must never cache.